Hello, welcome to Innovation Guru. In this episode, we are going to discuss what we call one-dimensional box. So this is a straightforward application of our Schrodinger equation. We have already seen what is Schrodinger equation, what is meant by operators, particularly Hamiltonian operator, what are eigenvalues and eigenfunctions, and what is normalization of wave function, etc. Now we are going to apply these concepts here for a particular problem, a particular situation. What is the situation? The situation is what we call one-dimensional box. This is a hypothetical situation to which we apply Schrodinger equation. This is a rather simplified problem or situation. It is not a real world problem. We are imagining a situation. Our world in this imagined situation is one-dimensional. So what a one-dimensional world means? We have a single dimension that of course is a straight line, and any body present in that system can move along that direction only. Right? Other dimensions are considered absent. So for convenience, we consider it as x-axis here. Okay. And our particle can move along this x-axis only. To and forth it can move. Okay. That is fine. Then again a condition is there. What is the condition? We call it as a box. That means the particle is confined within a particular region of space. Here we have only one-dimensional space. That means we have two walls at two ends of the box. In one-dimensional box, we have only two ends. And these two walls are having infinite potential. It means that the particle cannot penetrate the wall. Particle cannot overcome the potential energy barrier. That is the significance. The wall is shown by this bold arrow with a infinity sign here. Of course, in a one-dimensional world, that arrow should not be the wall. It will be a point in the one-dimensional world where the wall is infinitely hard point through which the particle cannot come out. That is its significance. If you imagine the physical picture, it will be like that. Here we have representing the infinite potential by the arrow and the sign. Both ends, this is true. So box has a length of L, start from 0, x is equal to 0 to x is equal to L, ending at x is equal to L. That is it. That is our one-dimensional box. So we can define the problem, our situation. Application of quantum mechanical model to a simplified system consisting of a particle moving horizontally within a box with walls of infinite potential from which it cannot escape. We can imagine it as an infinitely deep well also. Okay, now we want the solutions for it. Solution for Schrodinger equation. When we solve the Schrodinger equation, we will get values of E and psi that a particle can possess. E represents the allowed energy values. Psi represents the wave function. If you square psi, what we get? We get probability of finding a particle or locating the particle at a particular point within the box. Suppose we consider the midpoint and we evaluate psi at the midpoint, we find the square. So then the probability density at the midpoint is given by psi square. In order to do that, We have to define the potential energy, then put that potential energy into Schrodinger equation, then solve the Schrodinger equation. By solving the Schrodinger equation, we will define the wave function and we will define the allowed energies. First, we can define the potential energy. Assumption is that inside the box there is no other force, no other particle. So inside the box potential energy is 0. But at the wall of the vessel, potential energy becomes infinity. When x is equal to 0 or x is equal to L or x is less than 0 and x is greater than L. That is at the wall and beyond the wall. Potential is infinity on both sides. Schrodinger equation for such a situation we can put it as minus h cross square by 2m d square psi of x by dx square plus v of x into psi of x is equal to e psi of x. Psi is a function of x. Similarly, potential energy is also a function of x. Now we can explain the terms as well. H cross is simply h by 2 pi, that is reduced Planck's constant. M is mass of the particle. Psi of x, psi is a function of x. That is the wave function. We call it as time independent. We are considering the time independent Schrodinger equation here. And we put it as, we have put a term called stationary also. Stationary means the particle is having a wave function and it is having a corresponding energy, eigenfunction and eigenvalue. And its energy value will remain a constant, will remain as such. That is indicated by the term stationary. And what is Vx? It is potential energy. That is also a function of a position. X is energy. Energy should be a real number. Okay, now we can modify this equation here because we know at the wall of the vessel and beyond the walls there is no probability of finding the particle. That simply means psi is 0 at the walls and outside the walls. Then only psi square becomes equal to 0. And now we can consider the region inside the box alone. We did not consider the wave function outside. And inside the box, potential is 0. So we can write the wave equation by removing the potential energy term for the particle confined within the box. So it is put as minus h cross square by 2m d square psi by dx square is equal to E psi. And this is a equation, a standard second order differential equation. We can put these constants also. This is a minus h cross square by 2m that can be bring to the right hand side, of course. Then it will be a very standard second order differential equation and it has a standard solution. And from differential calculus, we directly go into the solution. The equation obeys the standard solution. That is psi x is equal to a sin kx plus b cos kx. A, b and k are constants. So this is not a complete solution for our wave function, or it is not a complete definition for wave function, because we have introduced into the standard solution 3 unknown constants a, b and k. Now we have to define these 3 constants. Then only the wave function will be complete or completely solved. In order to do that, we apply the boundary condition. We know x is equal to 0, psi becomes equal to 0, or x is equal to L, then also psi becomes equal to 0, wave function becomes 0. That's fine. and we put the condition x is equal to 0, then the wave function psi left hand side becomes equal to 0. Sin kx, x is 0, that means sin 0 will be 0. So this term also becomes equal to 0. But cos kx, cos 0 is 1. So this will be the second term becomes b. So that simply means 0 is equal to b, or the second constant, the constant b is equal to 0. So the second term in the wave expression vanishes and we get psi x is equal to a sin kx. We have simplified the wave equation now. One term has gone. We have defined the constant b as equal to 0. Okay, fine. Now we have to define a and k as well, the other two constants. In order to do that, we differentiate this wave function with respect to x 2 times. First differential, of course, ka cos kx, because differential of sin kx is equal to cos kx into k. Again differentiate, second differential, it becomes minus k square a sin kx. It is very obvious. Now we can have this sin kx, a sin kx, that is psi x itself. We can put that into equation number 6. What we get is d square psi by dx is dx square is equal minus k square psi. That's true there. Now we can combine this equation 7 and equation 2. Equation 2 is here. If you cross multiply and bring these two constants also to right hand side, then 2 and 7 can be equated, left hand side can be equated, then we can solve for k. Straightforward high school algebra only. Then we get k is equal to 8 pi square me by h square, the whole raised to half, or square root of that term. Square root of 8 pi square me by h square. Okay, we have solved for k. Now what we can do? We have the wave function given as a sin kx, and we have solved for k. We can bring the value of k there. We get it like that. Psi equals a sin 8 pi square me by h square, the whole raised to half x. Still it is not a complete solution because one constant is still remaining. Which is remaining? A is remaining. That is an unknown constant still. We have to solve for a also. To solve for a, we again apply boundary condition. Which boundary condition? X equals L. Then psi becomes equal to 0. Then our equation becomes, then our expression becomes expression for wave function. 0 is equal to a sin 8 pi square me by h square raised to half L. As a is not equal to 0, of course, the second term, sine function there, the sine term should be equal to 0. And we know a sine function is 0 only for integral multiples of pi. So this term 8 pi square me by h square, the whole raised to half L equals n pi, where n is an integer 1, 2, 3, etc. Then only this boundary condition will be satisfied. Okay. So then in the wave function, what we can do? We know this. We can 8 pi square me by h square, the whole raised to half will be equal to n pi by L, and that n pi by L can be brought into the expression for psi in this expression, equation number 9. So what we get? Psi equals A sine n pi by Lx. Okay. Now to solve this A completely, we use a concept called normalization of wave function. The wave function it is a solution for the Schrodinger equation, but it can represent the quantum mechanical system only when the probability of finding the particle within the given system is equal to 1. If the distance are not specified, we will have to integrate the probability function from minus infinity to plus infinity. But here the system, we have assumed that the particle is confined between the walls, that is from length 0 to L. So we can integrate the probability function, that is I square dx. Here we can take dx and integrate it from 0 to L, and that should be equal to 1. That is our normalization condition. So we put the wave function already obtained here. What we get is A square integral 0 to L sine square n pi x by L dx equals 1. That is our normalization condition. And we can solve that expression, and solution to that expression shows A equals, the equal to sign has gone from here, that is A equals square root of 2 by L. And we can bring it back to the wave equation, the wave function, that is psi equals square root of 2 by L sine n pi by Lx. That is our complete solution to wave equation. So wave function can have different values when you change the value of n. They are called the eigen functions. N is equal to 1, we get the first eigen function, n is equal to 2, second eigen function, and so on. And we can solve for energy as well. From this expression we can solve for energy, and also putting the value of L also there. Finally we can get from equation number 8 and 11, we can solve it, and we get En equals n square h square by 8 ml square. Combining equation 8 and 11, we will get this expression. So that is the expression for energy. So you put n is equal to 1 in both the expressions for wave function and energy, we get what you call the first stationary state. Corresponding eigenfunction and eigenvalue will be obtained. N is equal to 2, we get a higher energy state and the corresponding wave function. N is equal to 3, n is equal to 4, and so on. So the particle cannot have any desired value of energy. We call the condition as what we call quantization. Energy of the particle is quantized. It cannot have only certain discrete values given by this expression. When you put n values here, n is the only variable here. If L is fixed, if L changes, energy can change. As size of the box changes, energy also can change. Otherwise, energy depends on the energy state only, n value only. Okay. And also, the lowest value for n is 1. So the lowest energy will be En equals h square by 8 ml square. So that cannot be equal to 0. What does it indicate? The particle in the lowest energy state has some amount of energy, a finite value of energy for its kinetic energy, a finite value of kinetic energy. It indicates that it is called 0 point energy, and indicates that The particle is not at rest. It has some movement. And that is in accordance with uncertainty principle as well. If particle had zero energy and it is at absolute rest, we are knowing the position and momentum exactly. Or we are knowing its position in space and time simultaneously. And that is against our uncertainty principle. So, in quantum mechanical systems, particles do not have zero energy, but it have a 0 point energy which is not equal to zero. Okay, this is our first part. Now we have to apply this solution to some more cases, some more situations also. Then only the significances will come out. And we can see that size of the box also has a role in energy. The size of the box increases, L increases, the kinetic energy will come down. You consider the first level, the ground level. The energy will come down as size of the box increases. That is counterintuitive. When we are confining the particle to a smaller region, the particle will be wiggling more vigorously and it will be having higher energy, higher kinetic energy. But when the box size is increased, particle can move within larger region, then it will be less vigorously wiggling and its kinetic energy will be less. That is the significance. Another significance we can get from this equation. Okay, for the time being we stop here. We have to continue for some more time with the second part of the lesson. So, okay, bye, thank you.